Okay, let's do 2.8, finite dimensional normed linear spaces. Familiar setting to you because that's pretty much what sophomore linear algebra is about. You may touch on very much in passing infinite dimensional vector spaces and sophomore linear algebra, but predominantly finite dimensional vector spaces. Here we're talking finite dimensional normed linear spaces. Rn is an example of such. So many of the results we see in this section, though heavy on the analysis stuff, there's nothing really surprising that's going to happen in this section. When we go to infinite dimensions in the more unfamiliar setting, then some pretty weird stuff is going to happen. So in this section, we'll classify a normed linear space as finite dimensional by considering the topological property of compactness. We'll go back and look at our definition of compactness here when appropriate. Remember, Heine-Borel theorem deals with classification of a compact set of real numbers, or if you like, a compact set in Rn. So we're going to see Heine-Borel take a bit of a beating when we go to infinite dimensions. So the plan in this section is ultimately to address Heine-Borel type things in finite dimensions. So in this section, nothing terribly surprising. We've looked at norms. Kind of an in-passing comment here is some other kinds of norms. Each of the following is a norm on R2, and each of the following is easily extendable to a norm on Rn. We'll treat X, an element of R2, as the ordered pair X1, X2, thinking of it as a vector if we're doing the normed linear space stuff. The sup norm that you're familiar with, sup norm of vector X, that would be the infinity norm, sup norm. It would be the supremum of the components of vector X. Well, it ain't got but two components, so it'd be the maximum of those two components in absolute value, or in modulus if we happen to do a similar thing with complex numbers. So sup norm on R2, or for that matter, Rn max norm, it would become. The regular Euclidean norm that you use probably in sophomore linear algebra, the norm of a vector is the sum of the squares of its components, square root of. You can define it in terms of dot products as well, or inner products. The absolute value deviation norm, also called a taxi-cab norm, where the norm of a vector, actually we'll see this related to an L1 norm at some point in the future. That's the reason there's a subscript of 1 used there, is the absolute value of X1 plus the absolute value of X2 with the obvious extensions to Rn. Now, these different norms will imply different appearances, say, of the unit ball centered at 0. All vectors in standard position whose norm is less than or equal to 1 is what we have illustrated here in figure 2.3. The usual Euclidean norm, this just produces a unit disk centered at the origin. Again, all vectors in standard position with their tail at the origin. That means their head lies somewhere in this yellow disk under the Euclidean norm. Under the sup norm, the norm's determined by the maximum of the first or second component. So any vector for which the maximum of a component is less than or equal to 1 is a vector that'll lie in the unit ball. So unit balls need not be round. It depends on the norm. The vector 1, 1 is not in the unit disk over here, but it is in the unit disk under the sup norm. If the components are 1 and 1, and the maximum of those two is 1. So we can get components up to 1 in the x direction, the x1 direction, I guess I should say, or the negative of that since we take absolute values, or up to 1 in the second component, the x2 direction, plus or minus. And so under the sup norm, this is what a unit disk looks like, unit ball. Under the absolute deviation norm, like I said, this is probably the new one to you. We've used the other two. It's also called a taxi-cab norm. So let's elaborate on that. It's defined in terms of the sum of the absolute value of the first component with the absolute value of the second component. So if we wanted to look at this point right here, say the point 1/2, 1/2, or the vector with components 1/2, 1/2, that has an absolute deviation norm of 1 because you've gone 1/2 over and 1/2 up. If you go 1/4 over and 3/4 up, you'll also get a vector that lies on the boundary, a vector of absolute deviation norm 1, because you add together the absolute values of the components. The reason it's called a taxicab metric or taxicab norm is the idea of if you live in a city where the streets are laid out, say north, south, and east, west, there's multiple ways to get from any point to some 0.1 unit away. You can go over or go north and then east. You could go east and then north. You could go north a little bit, then east a little bit, then north a little bit more, and then east a little bit more. But being constrained always to travel on north, south, and east, west streets. So that's the reason that's sometimes called a taxicab norm or taxicab metric when treated as a metric. And here's 3 different pictures of unit balls under these various norms. So don't read too much into the concept that a unit ball is necessarily round. It depends on the norm or the induced metric. Okay, this comment is notationally a bit exotic. We're really just dealing with a finite dimensional vector space here. But this is a notation we'll use, and we got our reasons in the functional analysis. Throughout this section, set F is going to represent the set consisting of 1, 2, blah, 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 up through capital N. So it's a finite set with capital N elements. B of F is a set of all bounded functions on F. So function F is an element of B of F, which implies F takes elements of set capital F in, 1 through N, and gives out an element of field F, that 3 different F's, but a different font for each of them, gives out an element of field F, and we'll take field F to be the reals or the complexes in practice, such that the set F of S, such that S ranges over set F, is bounded. Okay, so here's what's really happening. Function F is defined on set capital F. So there's an F of 1 and F of 2 through an F of capital N. So there's a capital N tuple of field elements associated with each such function. Capital N tuples, that reminds me of Rn, or capital N, I suppose. So this is really, ultimately, if the scalar field is the reals, this is a complicated way of presenting Rn. But we want to look at it in terms of functions and bounded functions for reasons that'll become apparent when we deal with the infinite dimensional spaces. And we're making the requirement that F of S, such that S ranges over set capital F, is bounded. Of course it's bounded. It's just a set of capital N different field elements. Pick the biggest one, and that's the bound. We'll equip this set of bounded functions with a sup norm. By the way, it'll be a maximum norm because whenever we choose a function F, associated with it are capital N, say real numbers. Pick the biggest one in absolute value, and that would be the sup norm. So since we're dealing just with a finite set, I don't need the supremum. We get away with a maximum. Scrolling back to the previous page, rather similar to the statement here. When we were looking at a sup norm, hey, you've only got 2 components to consider, so we just take the maximum of those 2. That same observation holds here. We just take the maximum of the capital N components in absolute value or modulus. From section 1.4, we had introduced these delta sub I functions. Here we're defining delta sub I for I between 1 and capital N as delta sub I of S equals 0 if I is not equal to S, and equals 1 if I equals S, sort of like a characteristic function. So delta sub 1 is defined on all these values, 1 through capital N. Delta sub 1 of 1 is 1. Delta sub 1 of 2 and delta sub 1 of 3 and so forth is 0. The only time we get 1 out is when the index equals the input in the function, when those two parameters there are the same. So it's very much an on-off switch in that sense. The claim is these delta sub i's are basis of the bounded functions on set S. Since you take any f in B of f, it can be uniquely written as a sum from I equals 1 to capital N of f of I times delta sub I of x. So the of x applying right there. So a scalar multiple and then the function. Then that's a linear combination. Remember, this isn't as exotic as it looks. We're simply saying, hey, f of x, that represents a capital N tuple of, say, real numbers, field elements, complex numbers maybe. But it's just a capital N tuple of numbers. And what we do, say, when I equals 1, we pick out f of 1 times delta sub 1 of x. Well, delta sub 1 of x, that's going to be 0 except when x equals 1. So when I equals 1 and x equals 1, we'll get f of 1 equals a sum from I equals 1 to capital N, lowercase f of 1, delta sub 1 of 1, which really just reads f of 1 equals f of 1. And similarly, when we plug in x equals 2, we'll get f of 2 equals, well, 0 plus 1 times f of 2 plus 0 times f of 3 plus 0 times f of 4. It just picks those individual components out using this kind of characteristic function idea. So we're simply saying an n tuple equals the first component times a vector of the form 1, 0, 0, 0, 0, comma 0. Second component times 0, 1, 0, 0, 0, and so forth. So in some sense, these are just the standard basis vectors of R capital N. But these are written as functions, not as n tuples. What's a vector in a vector space? It's a thing that satisfies the definition of vector in a vector space. And functions can do that. It's just here we're representing n tuples using this function notation. So this is simply a somewhat exotic notation given your previous experience for a very familiar thing. We're ultimately just dealing with R capital N here. This is just an alternative way to present Rn using functions instead of n tuples. So we're going to shift gears now and talk about linear operators to a fair extent. The next result shows that a linear operator on a finite dimensional normed linear space is necessarily bounded. You didn't talk about that in sophomore linear algebra. Yeah, when sophomore linear algebra, almost exclusively finite dimensional spaces. Well, if sophomore linear algebra is about finite dimensional spaces, and we're about to show that linear operators on finite dimensional spaces must be bounded, there's no need to talk about boundedness. All linear operators in sophomore linear algebra were bounded if you constrained yourself to finite dimensional spaces, and I'm sure you did in the setting of linear operators. Linear transformations, possibly you call them. So there was no reason for this idea of boundedness to even be discussed in sophomore linear algebra. And if we stayed in finite dimensions in here, it wouldn't be an issue either. But we're here to do some infinite dimensional stuff. Proposition 2.28 says exactly that. For any normed linear space Z, all elements of the set of linear transformations from B of F as described above to Z are bounded. So all linear transformations from this normed linear space B of F, which by the way was equipped with a sup norm, to normed linear space Z, no constraints on it, all such linear transformations, linear operators are necessarily bounded. Let's go through proof of that. Okay. So we're in finite dimensions, and we want to establish boundedness. We're in finite dimensions for the domain of these transformations. So take T to be such a transformation. Let K be the maximum of the norm of T applied to vector delta sub I. The delta sub i's were in B of F. In fact, they form a basis for it. We commented above. So when we look at T of delta sub I, that would be an element of Z. So when we use these norm symbols, notice that we're talking about the norm in Z there. We've got two norms. We've got the norm on B of F, the sup norm, and we've got the norm on normed linear space Z. And probably sooner or later, we'll have the norm of the operator T. So if we take F to be in B of F, which has norm 1, yeah, we're using the sup norm, the infinity norm, on B of F. So we're taking a unit vector from B of F. You know you can represent it as this linear combination because the delta sub i's form a basis. Then if we take the norm of T of F, where F is a unit vector, right, we're going for a norm on T. Remember, we're trying to show T is bounded as a claim. If we look at the norm of T of F, then this would be the norm in linear space Z for the record. That would be the norm of T applied to the linear combination. Well, if we apply T to the linear combination, we can use the linearity to take the T inside the summation to produce this. So I did skip one step of linearity for T. Using linearity to, I want to use the word distribute, but that's not quite appropriate. It's using linearity to deal with that summation. T of the sum is the sum of the T's is what we've used, as I say. Here we've got a sum of a bunch of vectors in normed linear space Z. We can use a triangle inequality there. That's less than or equal to the sum of the norms, straight up triangle inequality. We can take this scalar, f of I, and bring it outside of transformation T. That's linearity as well. So we've used linearity twice, though I only explicitly stated that once. This is a scalar. The norm of a scalar times a vector is the absolute value of that scalar times the norm of the vector, the scalar property. So this is where it's important that the field be either the reals or the complex numbers. So we've got the norm of TF equals this. And remember, F was an arbitrary unit vector from B of F. Repeating that previous line. Hey, F was a vector with sup norm 1, max norm if you like, because we're in finite dimensions. So how big are the components F of I? At most 1. Since the norm, actually you should read sup norm, the sup norm of F equals 1. Then each of the components is less than or equal to 1. We chose K to be the maximum of these T's. Let me go back to the previous slide. I don't think I made a big enough deal of that. We define K to be the maximum of this collection of vectors. All right, back to the new slide. Each of these then is less than or equal to K. So we get less than or equal to K. We're simply summing from I equals 1 to capital N of K. That's K times N. K being determined by the maximum thing that we just saw, and N being determined by set capital F. So for an arbitrary unit vector, the norm of T of F is less than or equal to K times capital N. These are both fixed, K and N. So if we take a supremum over all unit vectors from B of F with this, that will be in turn less than or equal to Kn, and that supremum will be the norm of operator T. So we get the norm of operator T is less than or equal to Kn, and the claim was that such an operator is bounded. There you go, it's bounded by Kn. K is defined and N from set capital F. So, and we'll use this again later, linear transformations from B of F are necessarily bounded. Now we're going to look at compactness. The familiar Heine-Borel theorem states that a set of real numbers is compact if and only if it's closed and bounded. It doesn't say compact sets if and only if closed and bounded. It says compact set of real numbers if and only if closed and bounded. In the event you did your senior level analysis in Rn and not just R1, it would say a similar thing. It would be a set from Rn is compact if and only if it's closed and bounded. But there's places where Heine-Borel doesn't hold. It's infinite dimensional spaces. So you've probably never seen a set that's closed and bounded that isn't compact. If you have, you were in infinite dimensions. So we can actually get a classification of that. So this is justification, partially at least, of the comment at the beginning of the section. We'll classify compactness in a Heine-Borel sense in terms of finite versus infinite dimensions. But we'll see the Heine-Borel theorem violated in infinite dimensional spaces. Might point out quickly, Theorem 2.2.b says, if we have a compact set, then it's closed and bounded. But that's only half of Heine-Borel. If compact set, then closed and bounded. Heine-Borel says the converse holds. Closed and bounded implies compact for sets of real numbers or sets from Rn. So what we're going to do is show that closed and bounded subsets of B of F are compact. We've already seen B of F is a finite dimensional space. It's dimension capital N because we found a basis for it. So this is a converse of Theorem 2.2.b. So Theorem 2.2.b combined with this result shows that the Heine-Borel theorem does hold in B of F. Yeah, because it's finite dimensional is ultimately the reason that it holds, but we haven't established that. And let's check out our definition of compact. We said set K, a subset of a normed linear space, is compact if and only if either of the following two equivalent properties hold. You're used to this first one. Every open cover of set K has a finite subcover. And we also claimed, and I don't think Promislow establishes this, that this is equivalent to any sequence x sub n from set K has a subsequence x sub n sub k, which converges to a point in K. The second property is called sequentially compact. So we're actually going to use this second property more often. These have claimed to be equivalent. That Promislow I don't think shows, but we'd show that in the metric space setting in graduate real analysis. Graduate real analysis too, if we spend a lot of time on metric spaces. So we'll take this as given. But when we say compact, that's equivalent to saying sequentially compact. So if we want to establish compactness, we can just as equally well establish sequentially compact. So to the proof. So we'll show closed and bounded subsets of B of F are compact or equivalently sequentially compact. So let A be a subset of B of F, let it be closed and bounded, and let F sub n be a sequence in set A. So we're looking for a subsequence of sequence F sub n, which converges to a point in A, showing sequential compactness. For each I, think of I as a position in like a capital N tuple. We have F sub n of I, n equals 1 to infinity, is a bounded sequence. And these are all terms in set A, and set A itself is bounded by hypothesis. So this is a bounded sequence of real numbers or complex numbers, whatever your favorite field is. And we know that a bounded sequence of reals or complex numbers has a convergent subsequence. This property follows from, say, Weierstrass's theorem see specifically Theorem 2.14 in some of my analysis 1 notes. There's links in the online notes to those results. But in position I, we have a bounded sequence of terms. We've got the ith position of the first vector, the ith position of the second vector, the ith position of the third vector, but always the ith position. That's a sequence of ith positions, and they're all real numbers, they're complex numbers, and they're bounded. So they have a convergent subsequence. So we're going to let f sub n sub 1 of 1, for n1 equals 1 to infinity, be a subsequence of the sequence f sub n of 1 from n equals 1 to infinity. So we added a subscript on the index, moving to a subsequence. We know this subsequence must be convergent. So for any I, we get a bounded sequence which has a convergent subsequence. When I equals 1, pick that subsequence, f sub n1, n sub 1 of 1, the sequence of first terms, the subsequence of first terms, which you know converges by Weierstrass's theorem, Bolzano-Weierstrass theorem. That limit, define it to be f of 1. So we're looking for a candidate limit point. Define that to be f of 1. That was the first position. We just need to do it for all the other positions, and along the way guarantee that we really do get a subsequence of the original sequence. So what we're going to consider next is f sub n sub 1 of I, and n sub 1 equals 1 to infinity. This is bounded. These are all elements of set A, which is bounded. So we got a bounded sequence. Let's consider what happens when I equals 2. When I equals 2, bounded sequence in a setting where bounded sequences have convergent subsequences. So choose f sub n sub 2 of 2, n sub 2 equals 1 to infinity, to be a subsequence of f sub n sub 1 of 2, right? This subsequence up here with I equals 2. So pick that to be a subsequence of that first subsequence, which converges. So we're doing this nested subsequence stuff. When we're done, we'll have a way to describe the indices, and we'll have capital N subsequences of correspondingly f sub n of I subsequence, and they'll each converge. And that'll allow us to find a limit point of some subsequence of this original sequence. So similarly and iteratively construct subsequences, f sub n sub 3 of 3, f sub n sub 4 of 4, and so forth, up through f sub n sub capital N of capital N, which converge to something, denote the respective somethings as f of 3, f of 4, up through f of capital N. So for each index I, that is for each position, if you will, in the vectors, we have f sub n sub capital N of I, n sub capital N equals 1 to infinity as a subsequence of f of n, and it converges I-wise, component-wise, to the value f of I. We constructed the f of I vector in that manner. So we've created a subsequence that converges to an f of I. We're trying to show sequential convergence, sequential compactness. We chose an arbitrary sequence, f sub n, and we found this sequence, which converges for each I to f of I. So we need to show that convergence actually holds in B of f, under which we measure distances using soup norms. Well, we've got the set capital F throughout this section, 1 through capital N. It's a finite set. So the convergence for each I implies a uniform convergence over this set. We could go through the definition of pointwise convergence, choosing a capital N sub 1 for which we get within epsilon over capital N or whatever. We could go through component-wise. Since it's a finite set, we could do some sort of maximum capital N sub I deal to show that, hey, over finite sets, convergence with respect to each component, implies uniform convergence over the whole finite set. Wouldn't work if we had infinite sets. But we've got uniform convergence. Uniform convergence is equivalent to sup norm convergence. We made a comment about that. For the record, it was note 2.3.a. So this sequence, f sub n sub capital N of I, converges to f of I in b of f with respect to the sup norm. A is closed, so it must be that when we look at the limit of these vectors, that we get the vector f of 1, f of 2 through f of capital N must be an element of A. They're a limit point, and A is a closed set, so it includes its limit points. So we get convergence point-wise, component-wise, and hence convergence in B of F. And this is what the limit point is, and that limit point is in set A. We took an arbitrary sequence and a complicated way, but we created a subsequence which converges. And so we've got sequentially compact for set A, and that's part of the definition of compact as Promislow approaches it. Okay, let's look a little bit more at bounded linear operators. First claim is if T is a bijective linear operator from a normed linear space X to B of F, then T is bounded. All right, we showed something similar to that a couple of results back. What we showed is if we have a linear operator from B of F to Z, then it's bounded. So any linear operator from B of F to normed linear space Z is bounded. B of F is the domain up here. Down here, we've got a bijective linear operator from a normed linear space X to B of F, and we're drawing a conclusion of boundedness. So this one's different in that this time B of F is the codomain, whereas in proposition 28, B of F was the domain. And down here, B of F is the codomain. And we've got more hypotheses. We needed this to be a bijection. If it's a bijection, then it has an inverse. As you'll see, we use that in the proof. So let's go through the proof of 2.30. Of T is a bijective linear operator from the normed linear space X to B of F, then T is bounded. Let's do it by contradiction. Assume T is not bounded, assume T is unbounded. So we're looking for a contradiction from the definition of operator norm. For each n a natural number, there exists a unit vector, z sub n in X, such that the norm of T of Z sub n is greater than or equal to n. T is unbounded. In other words, we can find a vector. When we apply T to that vector, we produce something of large norm. We've got an unbounded operator. Think of the way you compute the operator norm. So we can make T of Z sub n as big as you want by choosing Z sub n appropriately. For such Z sub n, define X sub n to be Z sub n divided by the norm of T of Z sub n. All right. We're looking at sometimes a norm on normed linear space X, sometimes a norm on B of F. Whenever we see the T of, right, these would be norms on B sub F. I arguably could put infinities on these two, since these are elements of B of F. And we've got B of F normed with a sup norm. This new collection of vectors, X sub n, is a sequence in normed linear space X, and that sequence converges to 0 for the following reason. X sub n, we've defined it as up here, so when we take the norm of it, we simply get the norm of Z sub n divided by the norm of T of Z sub n. But remember how you define vector norm. These Z sub n's are unit vectors. So the norm of Z sub n is 1 divided by the T of Z sub n. We've chosen Z sub n in such a way that T of Z sub n in norm is greater than or equal to n. Take a reciprocal of both sides. 1 over norm of t of z sub n is less than or equal to 1 over n. That's what we get there. This holds for any natural number n. So when n gets large, this gets small, and so this norm must get small. And that's the reason we have the conclusion that sequence of vectors x sub n approaches 0. But if we apply t to x sub n, that is apply t to z sub n divided by this norm quantity, linearity allows you to bring the scalar out front, you know, abusing the notation a little bit, treating it as divided by that norm. So technically it's 1 over the norm times the vector. But we get t of z sub n times 1 over this norm. Hey, this is a vector divided by its norm. Well, then that's a unit vector, and that holds for each n. So here, the t of x sub n's are unit vectors. Up here, we see the x sub n's must approach 0. Now, and we're looking for a contradiction, right? We've assumed unbounded, and we want to establish bounded. Now, the set of all unit vectors in B of f has as its complement 2 open sets. This is everything except the collection of unit vectors. Think of it as a unit sphere, the surface of that sphere in B of f. We've got the interior of the closed unit disk, the open unit ball centered at 0 with radius 1, and the complement of the closed unit ball. So everything strictly inside the unit ball and everything strictly outside the unit ball. In other words, and both of those are open sets. So the complement of the unit ball, set of all unit vectors, is open. It's a union of 2 open sets. And the set of all unit vectors in B of f then is a closed set. And of course it's bounded. It's bounded in norm by 1. So this B of f is a closed and bounded space. Closed and bounded. That means compact. In finite dimensions it does, but not in infinite dimensions, as we'll see. We're in finite dimensions because we're having a conversation about the space B of f. And that was a space, in our notation, a space of dimension capital N. So it's a finite dimensional space. Well, then if you've got a closed and bounded set in a finite dimensional space, Proposition 29 told us that's a compact set. Or if you like, a sequentially compact set. And I like sequentially compactness. Well, then with a sequential compactness, there's a subsequence of t of x sub n, say t of x sub n sub k, put another index on the index n. And this converges to some y in the set of unit vectors B of f. Definition of a sequentially compact. I would really prefer to distinguish between compact and sequentially compact in the conversation, at least. When you hear compact, you really ought to be thinking every open cover has a finite subcover. But it's equivalent to this other idea. So we've got compactness, so we're using the sequentially compact idea. So we've got this subsequence t of x sub n sub k, and that converges to some y, also a unit vector. Okay. T maps x into B of f is bijective. We haven't used that yet. 1 to 1 and onto. T is linear. We were given that. So there exists an inverse mapping B of f into x. That's also bijective and linear. In other words, T inverse is an element of the set of linear operators from B of f to x. T inverse has as its domain B of f. And we saw in Proposition 2.28 some properties of such linear transformations that had as their domain B of f, they were bounded. So this T inverse is bounded by Proposition 2.28. By Theorem 2.6, when you have a bounded operator, you have a uniformly continuous operator. We've used that several times. Let's go back and look at it just in case. I think it's here. Yeah, Theorem 2.6 from section 2.4 said the following are equivalent. Linear operator T is bounded is equivalent to it being uniformly continuous on its domain. So that's the property we're using in this proof at this stage. So we've seen that T inverse is bounded. So T inverse is uniformly continuous on its domain on B of F. So T inverse of Y we introduced on the previous slide is the limit of that subsequence T of X sub n sub K. That's what Y was by definition. We know T inverse is uniformly continuous, so we can bring that limit outside of the T inverse transformation. That's where the uniform continuity is used. That gives us T inverse of T, bijections, so we can ignore that part, and we get a limit of X sub n sub K, X sub n sub K. And we know that the X sub n functions, the X sub n vectors sequence converges to 0. So this subsequence converges to 0. Let's go back and look on the previous slide at that. We had the X sub n sequence converges to 0. So any subsequence of that also converges to 0. Back to the next slide. So we must have the limit of the subsequence also equaling 0. But Y is a unit vector. Y is not 0. You can't have a bijection, and T inverse is a bijection. T inverse is a bijection. T inverse is a bijection. It can't map a unit vector to 0. If you like, apply T to both sides. T of 0 is certainly 0, and we'd have T of T inverse of Y being Y itself. We'd have Y equals 0. Y is a unit vector. Y is not 0. So this computation gives a contradiction. The only assumption that we made was that T was unbounded. That assumption must be false, and so T must be bounded. So we've got some ideas about linear transformations, linear operators on B of F, and bijective linear operators that are mapped into B of F. And the last result that I want to do in this video, not the last result of the section, just gives us some properties of finite dimensional spaces and operators on finite dimensional spaces. So let's go through proof of that and a reading of the statement. It says any linear operator, T, mapping X to Z, where X is finite dimensional, is bounded. All right, we had dealt with something along these lines earlier. We've definitely shown that for B of F, right? And we said this is the reason that you don't talk about bounded operators in sophomore linear algebra. So we'll go through proof of that. Secondly, all norms on a finite dimensional space are equivalent. Wow. All norms are equivalent on finite dimensional spaces, meaning if you have a finite dimensional normed linear space, then you can pick any norm you like because all norms are equivalent. That means all the same sequences converge, all the same topological properties hold, all the same limit properties hold. And second claim, all finite dimensional norm linear spaces over field F, the reals or the complex numbers, are complete. So completeness isn't a concern in finite dimensions. You might show completeness in the complex numbers based on completeness of the real numbers. That's something you would do in complex analysis. But finite dimensional linear spaces over the reals or the complexes, no problems there. We have completeness. And finally, any finite dimensional subspace of a normed linear space is closed, topologically closed. Okay. Some of these are touch lengthy, the final one's the shortest one, I think. So first, any linear operator T mapping X to Z where X is finite dimensional is bounded. So take yourself a basis for that finite dimensional space X. Notice the input space, the domain space of T is finite dimensional. So let E1 through E sub n be a basis. We know some properties of linear operators to and from B of F, as described from Proposition 28 and Proposition 30. So we'll introduce a linear transformation, J, that maps X into B of F. And then we'll introduce another transformation that maps B of F into Z. So we'll be going from X to B of F to Z. We'll do some composition stuff. So define J mapping X into B of F as J of E sub I equals delta sub I. Delta sub I was those basis elements we considered when we were looking at bounded functions on set F being the set of vectors 1 through capital N we used at that stage, but no problems there. So we're simply taking the first basis vector here and associating with the first basis vector here. Second basis vector here in X and associating with the second basis vector in B of F and so forth. Since J is a linear bijection from X to B of F, and since we've defined J on a basis for X, that determines everything. Justified by the following recollection from linear algebra. A bijection from a basis of one vector space to the basis of another vector space, which is exactly what we have, is in fact a bijection between the vector spaces themselves. This is how the proof of what I call a fundamental theorem of finite dimensional vector spaces goes. More of that later. We'll look at some supplemental notes and talk about the fundamental theorem of finite dimensional vector spaces, which simply says if you have a dimension n vector space over the reals, you've got the vector space Rn, and that works for any field, in fact, Fn. But we're defined J that maps basis elements of vector space capital X to basis elements of B of F, choosing these to be of the same dimension. So J inverse exists because we just made an argument that J is a bijection. So we can talk about J inverse mapping B of F into X. This exists. It's linear, inverse of a linear transformation when the inverse exists is linear. And if we take T composed with J inverse maps B of F into X, T maps X into Z. So this composition will map B of F into Z. Composition of linear operators is linear. So we get the linearity. Here we've got the domain as B of F. And we've seen if you have a linear operator whose domain is B of F, that finite dimensional space, then it's a bounded operator. So T composed with J inverse is bounded. J itself is bounded. Let's see, J maps X into B of F, right? Notice the difference here. We got B of F as the domain here and as the codomain here. J maps X into B of F, and J is a bijection. Proposition 230 told us under those conditions, bijection with B of F as the codomain implies boundedness. So Proposition 230 tells us that J is bounded as well. So we've got TJ inverse bounded, we've got J bounded. Of course, we can write T as TJ inverse composed with J, all these compositions here. Proposition 2.8 would tell us that the norm of T is less than or equal to the product of the norm of this times the norm of that. This is bounded, that's bounded, so the norm of T is bounded. And there's the boundedness of T, and that was the claim. So the claim was operator T is bounded in this setting of finite dimensional domains, and there's the proof. Secondly, a couple of claims on this one. All norms on a finite dimensional space are equivalent, and all finite dimensional norm linear spaces over the reals or the complex numbers are complete. So two claims. First claim, equivalence of norms. Second claim, completeness. For the equivalence of norms, let norm 1 and norm 2 be norms on a given linear space X. We've done this kind of thing previously in some proof, let T map norm linear space X with respect to the first norm into norm linear space X with respect to the second norm, and define T as an identity map. So it simply takes X here to X there, but you measure distances differently. You got different norms on those two spaces, though it's the same set of vectors. By part A, we know T is bounded. We're dealing here with finite dimensional spaces. We just saw norm linear transformations on finite dimensional spaces are bounded. So we get the boundedness from previously. Take X sub n to be a sequence that converges to X with respect to the one norm. Remember, we defined equivalence in terms of stronger and weaker, and that was defined in terms of whether sequences converge or not. So what we're going to do is take a sequence that converges with respect to the one norm. We're going to show it also converges with respect to the two norm, and that'll show the two norm is weaker than the one norm. And this is a perfectly symmetric situation. We can interchange the roles of the two norms, and then we'll get that that weakness implication is reversed. And that's how we'll draw the conclusion of equivalence. So X sub n converges to X with respect to the one norm. That means by definition, for all epsilon greater than 0, there exists a capital N, a natural number, such that when the index lowercase n is at least as big as capital N, we have the one norm of X sub n minus X less than some little positive quantity. Let's take for our little positive quantity, epsilon divided by the operator norm of T. You know, it's bounded, so whatever parameter that is. But then if we take n greater than or equal to capital N, then we have the two norm of X sub n minus X. That would be the two norm of T of X sub n minus T of X. Remember, T is the identity transformation. So that's just substitution in the fact that T is an identity transformation. Linearity allows us to write that as T of the difference. The difference of the T's is T of the difference, as I say. Still measured with respect to the two norm. Note 2.4.a says if we have a norm of T of a vector that's less than or equal to the norm of the operator T times the norm of the vector. And here you see all three of the norms under conversation. Note 2.4.a implies exactly this, though I don't think it says it with quite the enthusiasm that we do here. We can tell we've definitely got three norms. Here's the norm in that space, X with the two norm. Here's the norm in that space, X with the one norm, and there's the operator norm. So definitely three different norms there. And we just said if n is sufficiently large, then this one norm is less than epsilon over the operator norm T. So if we'll substitute that in here, we see we get this to be less than epsilon. In other words, if n is greater than or equal to capital N, then the two norm of X sub n minus X is less than epsilon. That is, the sequence X sub n converges to X. The sequence X sub n converges to X with respect to the two norm. So any sequence that converges with respect to the one norm also converges with respect to the two norm. That is, the two norm is weaker than the one norm. Remember, for an informal understanding or an intuitive understanding of stronger and weaker, think of strength as stopping sequences from converging, as we discussed previously. So the conclusion is the two norm is weaker than the one norm. We can take T as the identity, but mapping the set X under the two norm to this set, typo there, set X under the one norm. Take that as the identity. You end up ultimately just interchanging the roles of the one norm and the two norm, and you can also draw the conclusion that the one norm is weaker than the two norm. Since each is weaker than the other, that's the very definition of equivalence, and so those norm 1 and norm 2 on finite dimensional space, capital X, they're equivalent in the sense of equivalence as defined previously. Second claim in part B is all finite dimensional norm linear spaces over these fields are complete. So it's a claim of finite dimensional spaces being complete. So secondly, we'll address completeness. We know B of F is complete under the suit norm. We addressed this previously. Yeah, it was in the previous section, I think, Theorem 2.14 for the record. So let X, with a given norm, be a finite dimensional normed linear space, and let X sub n be a Cauchy sequence in that space. Definition of completeness is Cauchy sequences converge. So we need to find a limit for this Cauchy sequence that's in this space. We know a lot of stuff about operators. So define operator J, mapping X into B of F, as we did in part A. We map basis elements from one to basis elements of the other, right? We're dealing with a finite dimensional space here. So take a basis and associate the basis elements as we did a few slides back. As we argued there, J is bijective and bounded, as we saw in part A, and so uniformly continuous. Remember, boundedness of a linear operator implies uniform continuity. Theorem 2.6, we looked it up from one of the previous sections a while ago. So sequence J of X sub n we're claiming is a Cauchy sequence in B of F, because if we take J of X sub m minus J of X sub n with respect to the suit norm, so a sequence in B of F, linearity gives us J of X sub n minus X sub m, J of the vector difference, X sub m minus X sub n, linearity with respect to the suit norm. Note 2.4.a, again, tells us that's less than or equal to the norm of the transformation times the norm of the vectors. All right, we got three different norms here, a little less clear. We got the suit norm. That's because we're talking about B of F for those vectors. We've got the operator norm, because J is an operator. And this is also a norm linear space norm. This is a norm in this linear space. That's where the vectors X sub n and X sub m came from. So you want to make this small? You want to make this less than epsilon by making the index sufficiently large? Not a problem. You can do it for this because the X sub n is a Cauchy sequence in this norm linear space. So you make the index sufficiently large, you can make this small. You can make it smaller than epsilon over the norm of J, for example, similar to what we did above. This can be made small. This is a constant. This can be made small, to be informal about it. And so this tells us that J of X sub n is a Cauchy sequence in B of F. But like we said, we saw above that B of F is complete under this suit norm, this infinity norm. So Cauchy sequences converge in B of F. This is a Cauchy sequence in B of F. So it converges to something, call this something Y. So there's some Y in B of F such that this Cauchy sequence converges to Y. And we're trying to establish completeness of this normed linear space. We need to show that arbitrary sequence X sub n converges. We took this sequence X sub n, Cauchy, in this normed linear space. We want to show it converges. Okay, so we've got what? We got a bijection here and a Cauchy sequence that converges. Bijections, here comes inverse transformations, I bet you. Let's see, J should be J. J is bijective and linear, as we saw. Forgive me, another typo there. J is bijective and linear. So J inverse, mapping B of F into X, is also bijective and linear, and that's where the bijection argument is used. It came out of the mapping of the bases, as mentioned earlier. If we have a bijective linear transformation defined on B of F, then, I'm not sure we need the bijective for that part. Yeah, we did, proposition 230. So bijective and linear, then this is a bounded transformation. So J inverse is bounded. So we can take X sub n minus J inverse of Y, write that as J inverse of J of X sub n, because that's just the identity. Same second term, so I can't argue with the equality here, what we're up to here might be a bit concerned. We'll resolve it shortly. This vector difference, norm of, equals this vector difference, norm of. We simply put an identity in there. Hey, linearity of J inverse. So we can write this as J inverse of J of X sub n minus Y. We just observe that J inverse is bounded. So we can talk about the norm of that using the inequality here, again, coming from note 2.4.a. Linear transformation applied to a vector is less than or equal to the norm of the linear transformation, linear operator, times the norm of the vector. Again, 3 different norms. These two look a little bit alike because they don't have subscripts on them, but this is an operator norm and this is a vector norm. The vector norm in the space, capital X, we were denoting it. We just saw, previous slide, J of X sub n was a Cauchy sequence that converged to Y. We chose Y to be the limit of it. So this can be made small by making n large. So this can be made small by making n sufficiently large. This is a sequence. This is just some vector. Oh, that vector must be the limit of this sequence. We get J of X sub n minus Y in sup norm to approach 0. Let's see, that's from over here. J inverse is bounded. Here we go. So X sub n must approach J inverse of Y. This must approach 0 as n approaches infinity. And so X sub n must approach J inverse of Y. That is, sequence X sub n converges. We took an arbitrary Cauchy sequence in the space, and we showed that that Cauchy sequence converges. We even found its limit. It's J inverse of Y, and we explicitly said what the J was. Arbitrary Cauchy sequences converge. That's the definition of completeness. So this normed linear space is a complete normed linear space as claimed. Finally, for this theorem, claim is any finite dimensional subspace of a normed linear space is closed. So take X, normed linear space, to be a finite dimensional subspace of some given normed linear space. By part B, we know finite dimensional spaces are complete. So we've got a complete normed linear space. We got a Banach space. We could treat this as a subspace of itself and then employ theorem 2.16, which said a subspace of a Banach space is itself a Banach space if and only if it's closed. And that's where the closure comes from. So that gives us the closed conclusion, and finite dimensional subspaces of normed linear spaces are closed. And that's where I want to stop this video. We got a little bit more to do. We're well past halfway through this section, but let's call it quits there. We'll come back and finish this again in a brand new video. I'll see you there. Have a nice day.